this is quantum computing part 7. All 6 parts, including a primer, is on there. So there's 7 videos, and then this will be video number 8 on that playlist. I have other discussion series like path integration and Lagrange mechanics are there. We started general relativity, and E&M got like 8 lectures in, and then we stopped. So we'll pick those up again at a later date. But now we're on quantum computing again. So last time we talked about... Is this all
chapter 1?
This is all chapter 1 still. Yeah, chapter 1. This is part 5, chapter 1. There's a lot in chapter 1. So last week we talked about P versus NP, where we had polynomial time versus non-deterministic polynomial time. We talked about how that works in complexity theory and how that shows up in NC, and how that shows up in quantum computing. And there's just one takeaway that I wanted to talk to you about. That was the kind of like the you know, everything that we've waited for with the complexity theory and why this stuff matters. And that was that factoring. As many of you know, factoring is kind of like one of the main things that we want out of quantum computing because it seems to be really good at it. That's just something that the quantum computing is really good at, is factoring. Factoring is thought to be NP. To be an NP problem. Now, it is not known if it is NP complete. But one of the rules of being NP complete is if you can solve an NP complete problem, you can change that problem parameters and solve any NP problem. So here's the cool thing about quantum computing, is quantum computing knows that how to do factoring. That's something that we've got pretty under control. Is factoring is solving a factorable problem with a quantum computer, or at least in theory. Maybe not in practice, but at least in theory, right? So now, if factoring turns out to be NP complete, then quantum computing, I should say big if factoring is NP complete, then we know how to do all NP problems using a quantum computer, which is really, really cool and exciting because what are the NP problems? Well, there's encryption, which is kind of obvious, but then there's also like protein folding, working on, there's several solutions or several problems working on curing cancer that are NP complete or NP problems. There's lots of problems that show up in computational physics that are NP problems. And if we can prove that factoring is NP complete, then there's a good chance that we can prove that we can solve, all NP problems with quantum computing, which is a really big deal, okay? A really big deal. Okay, so that was what we did last time. This week we're going to talk about the Stern-Gerlach, okay? Now there's a lot of, like I said, there's a lot of words for this one and not so much stuff to put on the board. So if you would like to follow along with the notes or just listen, that's fine either way. But we are going to be drawing some stuff, and I got some demonstrations and stuff to show. But the Stern-Gerlach experiment. So the first experiment of the Stern-Gerlach was proposed by Stern in 1921, and it was carried out by Gerlach in 1922. It was a situation where he had an oven that would heat up silver atoms. That was the first one. He'd heat up silver atoms. And then it would send them out in a beam into a magnet. This would be called the SG machine. And as the atoms would go through the magnet, they would be deflected. Okay? And then each of those positions, so as they get deflected, each of those positions was recorded for that deflection, so that you could measure the angle. This was the original one carried out in 1922. Okay? Well, in 1927, there was another one, a more refined one, that came along, where they did hydrogen atoms. What's so special about hydrogen atoms? Well, let's talk about it, okay? Hydrogen atoms contain a proton and an electron. Okay? So the electron orbits around the hydrogen proton in an orbital, an s orbital, but it's not like. So there's been like a lot of trucks going by lately, delivering wood. I don't know why. But it doesn't orbit like a classical orbit. So like if you think about the planets like a sun, right? A sun and a planet system, right? You might think that the planet orbits around the sun and, a period of orbit is, one time that it goes all the way around. But in quantum mechanics, things don't work that way. Classical intuition does not work anymore. So, what really happens is that the orbit kind of exists everywhere at once. It's a plane wave. It's spread out. So instead of like a ball going around, it's more like, a wave that makes up the entire orbital. Okay? Now this was kind of known at the time, right? But what's so special about the fact that it orbits like that? Well, let's hold on. We'll get into it in a second. But anyways, because it does orbit and it goes around the nucleus, there's a little bit of a magnetic field, right? A current carrying wire will have electrons or charges moving in it, and a charge moving in it will generate a magnetic field around the wire. This is all electricity and magnetism done in the 19th century. Easy breezy, right? Well, as this goes through the magnet, this magnetic field that's made by the motion of the electron will interact with the SG apparatus, and that's what causes the deflection itself. Okay? Preezy. Easy breezy. A solenoid, so a solenoid would be the opposite. So if you had a coil of wire, much like our handy-dandy Tesla coil that's not connected anymore, that I have to reconnect. But if you had a solenoid, wrong camera, like this Tesla coil, then it's a wire that's a coil that has current going through that coiled up wire, and then the magnetic field runs this way through it. So this would be the B field through a solenoid. So it's the same concept, it's just the opposite. This is the current carrying wire, so magnetic field runs around. This is a current carrying coil, so the magnetic field goes through. Okay? But same concept, right? But yeah, so then the magnetic field that generates from the orbital electron would interact with the magnetic field of the box here, and then this would cause the deflection, okay? Right, induction, yeah, very good. Okay, so the magnetic field depends on the electron's total momentum, right? That's what we know. We know that there's a total momentum. So here, again, consider the two system of planets, right, orbiting, or the sun system orbiting, right? The total momentum of the planet is going to be not only the planet orbiting, but also the planet spinning, right? We can add all of the angular momentum of the spin plus the orbit, and that's the total momentum, right? So now we get into the fun part with hydrogen. Why is hydrogen important? Well, hydrogen, specifically, because it has one electron that's all, spread out along the whole orbit, has zero orbital momentum. So here's what they did. They thought that if they put the hydrogen beam into the SG machine, they expected to see a straight line. Okay? Here's a couple things going on, right? If I take these balls and I just throw them, okay? Just throw them, right? What am I seeing here? I'm just throwing them, and there's going to be all sorts of variations with the throw, right? This is a classical intuition of throwing something. Now think about the classical intuition of having a charge on these, okay? So you charge them up. Really good, okay? And really good charge, okay? You get them really, really good, whatever that's supposed to mean. And you send them through a magnetic field. Well, depending on how they get charged and how they're spinning, you would expect to find a whole pattern, a vertical pattern of where they land on the board, right? Somewhere along here, as I throw them, they're going to be interacting, ooh, don't fall. They're going to be interacting with the magnetic field, and they're going to land anywhere on that board, in that vertical line, right? So that's what you'd think if they interact. Okay, so then you'd expect to see kind of like a whole slew of angles here, right? That's if they interact, if there's orbital momentum. But they don't expect to have an orbital momentum because in a hydrogen system, there is no orbital momentum. So they expect to see one line coming out and hit the center and not hit anything else, right? But what do they see? They see neither. They don't see this.
I would like to have some orbital momentum.
I don't have any to give, unfortunately. Tyrion does. He's spiraling out of control. Oh, okay. Anyways, but what they saw was instead that as the hydrogen atoms hit the magnetic field, they were deflected into two distinct places. So again, they didn't see this, and we call it SGZ because it's oriented on one axis. We just call that axis the z-axis. They see two lines, two spots of impact, which is really strange. Two different energy levels. It's not so much energy because they could be degenerate, but what happens is it's spin, okay? Now, I haven't even been following my notes. I don't even know where we're at. I just know I love this talk. This is like one of my favorite ones. So, anyways, so you could think of them as a spin up and a spin down. But this has a couple major implications, right? First was that how do they go from thinking of seeing something spread out to then being like, okay, well now we're gonna put no orbital momentum, so it shouldn't have any interaction at all, to having discrete. Well, if something doesn't have orbital momentum, then it's possible that it could be spinning, it could be rotating, right? So they thought, okay, well let's just call it spin because this is how it behaves. But here's the other thing. It's discretized. Did I spell discrete right? Something like that? It's discretized. Meaning that there's only two, well, for this situation, there's only two answers. Right? Spin up and spin down. That's it. They took this, that's how they got from saying, okay, well, it's not a straight line, which would mean there's no extra momentum, or there's no spin momentum. And then saying, okay, well, if there is spin momentum, then why isn't it just spread out? Well, there must be two things. It must be discretized. Okay, so now discretizing spin is not too strange. It's like, by this time, Einstein has already said light can be both a particle and a wave. Like, this is a thing that Einstein said. And then everybody was like, I don't know, Einstein, you are pretty smart, but still. And then now, by the 1920s, this is definitely a thing. Discrete particles and waves are a thing. So it's not the strangest thing to think, okay, what if momentum is discretized as well? Okay, so now here comes the thing that I've promised you. They said, there must be this magical spin. So let me tell you something that physicists refuse to tell people. I'm going to tell you exactly what spin is. Okay? Physicists just don't do this. So you guys should be really in for a treat with this, okay? So listen closely. This is what spin is. I'm going to read from my notes directly. What spin is: a quantum number that explains the discrete deflection angles observed in the SG experiment. Okay? That's what spin is. And then I'm sure there's audible boos. Let's talk about what spin is not. Literally something spinning. right? That's what we have found out from our studies in physics, that is not something actually spinning. And really the only way we know how to describe it thus far is a quantum number that explains discrete deflections, angles observed in the Stern-Gerlach experiment. Right? That's it. We see this stuff. We know it exists.
That is what spin is postulated to be, or theorized to be.
I feel like people are going to get mad and leave now. Hey, Tim, good to see you. Good to see you. Yeah, so that's the best we can do with spin right now. We don't know. We want to have a classical intuition of it. We want to have something where, we can relate it to everyday experience, that we could, think about in terms of our classical, our way of understanding things. But alas, we don't know anything other than that it is a quantum number that explains the phenomenon that we see. Okay? And it explains it accurately. Okay.
I mean, that's just your spin on the subject, Matt.
Get it? Do you get it, everyone? That's just my spin on the subject? Yes. Okay. Anyways. Okay, now, we're almost done. I want to show you the cool phenomenon. The cool thing about Stern-Gerlach. Then they did this. Then they took this hydrogen experiment and they said, let's do a couple things with it, okay? Let's talk about two machines. So they dove from the oven of hydrogen atoms into the first Stern-Gerlach machine, oriented in the C direction. It splits up. It splits up into two different states, a spin-up state and a spin-down state, okay? So we'll say the spin-down state looks like this, and we're going to put a screen in front of the spin-down state so that we're only measuring, so just think about the bottom half of this thing, right? So now we're only measuring the down spin, okay? I don't know why we're at Z1, it's supposed to be Z minus. So we let the spin-up particles go through, okay? We put them through another Stern-Gerlach machine, but this time oriented it sideways. Take it, turn it 90 degrees, now it's in a different coordinates, or different direction, we're gonna call it the X direction. And we get what? Well, you get two beams. Okay, you might think at first like, okay, well, if we measure it in spin, in one spin direction, then that's the direction of the particle is spinning and that's it. Like if you look at something, and it's spinning, like, like this, then it's spinning in one direction. So you've measured the way that particle is spinning. That's it. It's done. You've measured it. You've oriented it so that it's spinning this way. So what happens if you look at it in a different dimension? Well, you don't see it spinning in that dimension. You see it spinning in the other dimension. But here we see that, okay, well, now we're back to spinning up and down in our representative, in our dimension, in our SGX dimension now. Okay, well, that's pretty strange, but, it feels weird, man. It does. It feels weird. But that doesn't mean that this is the end of the story. Okay, so maybe quantum particles could have something a little bit different. Something that doesn't, it could be spinning one way and then you remeasure it and there might be some interaction, there might be something else. Okay, no biggie. Let's block the spin down particles now. Okay? Send it to a third SG machine. And we're going to reorient it back in the SGZ. Twitch, what do you think? Twitch chat, I'm talking to you. What do you think is going to happen if we remeasure what comes out of here? Do you think we're only going to get the SZ plus particles, the particles that are spinning upward in the Z direction? Do you think that, we're blocking off the minus particles. There's no X minus particles going through. Linus, you're right. You see both ZX and Z minus. For some reason, once we reorient the machine into the X direction, we see Z plus and Z minus again, even though we've already blocked off the Z minus. It's like it doesn't even matter at this point. Well, it does matter in some sense because we're kind of cutting down the intensity by 1/2 every time we go through another SG machine. I mean, here we cut it in half. Now we're into a quarter, and then you can divide by 2. Right? So this is just really crazy that we see this. This is not like something that you would imagine, especially classically. This is just so weird. There's one more way to do this, where you take this middle section and you block it off to measurements. It's very complicated. We're not going to get into it. It's in the way I know it from Townsend, but it's not at all like intuitive, and it doesn't help us discuss why this is relevant to quantum computing, so we won't go into it. But if you're interested, look up in Townsend the next step of this, and you'll get to see the Feynman's idea of how you don't measure the inside, you just reorient it in the oven. It's complicated. There's also a matter of where things get measured, so it's not at all like a straightforward endeavor. But it's in Townsend. Townsend does a really good job laying it out. It's very good. So if you're interested, check there. Now, how does this relate to quantum computing? Well, let's kind of try to treat this like a quantum computer. So we're going to assign the down or the up state in Z to a state 0. Okay? We're going to assign a state down in Z to 1. So what does this mean? Well, what if we also write a new basis? So we'll take this into a new basis. So here's the math you wanted, Tyrion. So we'll take the x up state and we'll send it to a superposition of 0 and 1, which we know it kind of has to be, right? In order to measure what we actually measure, it's all divided by root 2 for normalization purposes. X minus, that's how we get the probability of 1/2. 0 minus the 1 state over root 2. Okay. So now we have our Z up, Z, no respect. Our up state, our down state in the Z, and then we can also write it in a new basis, which is up and down in X, and this is all perfectly fine, okay? So let's break this up. Let's call this process 1, this process 2, and this process 3. If this is our quantum computing, how do we, how do we talk about the steps through this? So let's look at step 1. Step 1 is going to be, we measure, or we know about SZ plus, because we measure SZ minus, so the other state is still going. So we're going to assign this to be in a 0 state, okay? So now after we do this blocking off, we have a 0 state of particles going into the SGS machine, okay? Good. Nothing crazy. Step 2, we block off X minus, okay? So step 2, we block off X minus, and we have the state X plus. That remains, and we'll be continuing through our quantum computer, right? So then we have 0 plus 1 over the square root of 2. And again, we're changing basis. We want these to still represent the Z's. So that's why they both show up in X plus, and it doesn't just go to a 0 or 1. Which does make it kind of tricky when you're actually doing quantum computing stuff, because, yeah, pretty much you only ever talk about 0s and 1s, so when you change bases, it's kind of difficult to keep track of sometimes. Okay, but lastly, now, if we look, we want to talk about 3. 3 is the weird thing, right? 3 is super strange. How do we get to this thing where we get both Z plus and Z minus? Well, actually, we're kind of already set up for it. Look at this. What is the 0 state? Well, that's just Z plus. So our final state for 3 is just going to be this again, right? 0 plus 1 all over root 2, okay? So now this is the final thing we get at 3, is just this superposition of Z plus and Z minus over root 2. I didn't write it like that. I should have written it like that. Z plus and Z minus over root 2. There we go. So you know that if you come to here and you start measuring particles, you're going to get Z plus with 1/2 probability and Z minus with 1/2 probability. So our quantum computing setup actually works really well with the Stern-Gerlach machine. However, we don't know, like, I was kind of joking about the whole spin thing with physicists. We don't 100% have a great idea of what spin actually really is, especially physically. We have a mathematical understanding of what it is. So right now, our mathematical understanding is that the Stern-Gerlach machine is an excellent, excellent use of quantum computing. Like, you can measure it perfectly fine. All of these states look just like qubits. Wonderful. Will nature tell us something else more about it? Possibly. And it requires more and more experimenting, more in theory, and more quantum computing theory about, you know, what type of experiment works well, and then you got to build the experiment, test the experiment, use the experiment. That's it. Quantum computing part 7, done.